My dear student, colleagues, and all the viewers for watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. Good morning to all. So hope you are well and safe from Corona pandemic. So as we know that we are staying in a Corona pandemic situation, and recently the situation is becoming worse. So we have to maintain our health rules. So I think we have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. And we have successfully completed our 198th international physics webinar. And today it's our 199th. And we have with us here today our respected Professor Dr. Jiban sir, Professor Department of Physics, Bangladesh University of Engineering and Technology, BUET, Dhaka, Bangladesh. And he has already connected with us, so I'd like to welcome our speaker. Sir, namaskar and good morning and welcome to our International Physics webinar. And thanks for accepting our invitation, sir. So before going to you, sir, I'd like to introduce you with our student and viewers, though everybody know you well. So they are student and viewers. So we have divided our webinar into three parts. First of all, I would like to introduce our speaker with all of you, and then our speaker will deliver his speech, and at the end we have a discussion session. In that time, anybody can join with us. So I think you have already come to know the title of this today's International Physics webinar, at least the metal oxide thin film, state of the art and process. And our speaker is Dr. Jiban sir, Professor, Department of Physics, Bangladesh University of Engineering and Technology, BUET, Dhaka, Bangladesh. And we can see Dr. Jiban is a professor of physics, Bangladesh University of Engineering and Technology, Dhaka, and where he has been teaching since 1989. Dr. Poddar was born in Narayanganj, Bangladesh on 24th of December 1959. He received his bachelor degree and master degree in physics from University of Dhaka in 1980 and 1981 respectively. Dr. Poddar received his MPhil in 1987 from BUET and PhD in physics from BUET in 1994 under the research collaboration of Anna University, India. Dr. Poddar joined at the Bangladesh Atomic Energy Commission as a scientific officer in 1987. He was appointed as a lecturer in the Department of Physics, BUET, in 1989. He became an assistant professor in 1992, assistant professor in 1998, and full professor in 2002. Dr. Poddar pursued postdoctoral research at Anna University, India during 2000-2001, and Nagua University of Technology, Japan, under JSPS fellowship during 2003 to 2005. Professor Poddar served the Department of Chemical and Biological Engineering, University of Saskatchewan, Canada, as visiting professor from 2012 to 2015. Dr. Poddar's area of research interests include growth kinetics, nonlinear optics, optical crystal, compound semiconductor thin films, nanomaterials, carbon and carbonaceous and materials for optoelectronic and photonic application. Dr. Poddar has supervised so far about 16 MSc and 28 MPhil and 5 PhD students. Professor Poddar has evaluated over 160 PhD theses from different universities around the world. As of 2020, Professor Poddar has published over 165, and within this year, he published almost 20 research articles in the different referred journal and proceeding. So thanks again. I think you will enjoy this lecture, and thanks again our sir for accepting our invitation, and thanks me actually to give me opportunity to arrange such an important webinar. And I would like to say thanks again, sir, that when I have started this webinar, so maybe in 2020 in June, 1 year ago, actually sir helped me lots in doing this, and by your help, today we are going to celebrate our 199, and in today's evening we are going to celebrate our 200th webinar with Nobel Laureate. So thanks, sir, for everything. It's your time, sir. You can start your session, sir.
Thank you, Dr. Pretam Kumar Das, for inviting me to this international webinar on the physics Adda. You are celebrating this seminar is 199, and good morning to the audience, dear friends, dear colleagues, all my research scholars. So I'll talk about today the metal oxides, thin films, the state of the art and approaches. So we know that the importance of the thin films and the metal oxides, especially these metal oxides, the thin films are well known and widely used in the fabrication of sensor and biosensors. So these in the recent years, the nanotechnology has opened new applications of metal oxides. Reducing the grain size to nanoscale increases the active surface area and induces new effect due to the quantum confinement, such as the band gap widening, room temperature, photoluminescence, etc. So these the metal oxides widely used for last few decades for fabricating that sensor materials. So we know that the metal oxides are divided into two groups, mainly the transition metal oxides, non-transitional metal oxides. So these are the all common ferric oxide, nickel oxides, chromium oxides. And here the pre-transition metal oxides is aluminum oxides, magnesium oxides, post-transitional metal oxides like the zinc oxides, tin oxides. So there are the class of the metal oxides includes that alkaline metal, earth metal oxides, transitional metal oxides, poor metal oxides, rare earth metal oxides. So the series of metal oxides are available abundantly in the nature. So important thing is actually these metals behaves the insulator. If the D shell contains the odd number of electrons, like the titanium dioxide, tungsten oxide, vanadium oxides. So these group of materials shows actually although they are the metal, but behaves as the insulator. So this class of materials are widely used in the recently for fabricating the biosensors and gas sensors. So you see that look at the actually periodic table. Here, these are the class of materials: cobalt oxides, manganese oxides, tungsten oxides, cerium oxides. Rare earth metal oxides have strong correlations among their 4f electrons and participate in bonding. But the D shell, this contains the odd number of the 7, 5. So these odd number of electrons in the D shell, especially these group of metals, behaves the insulator. So here our interest actually to discuss about the application of metal oxides, and I will give you the presentations in a very clearly to the beginners to have a very clear understanding about the subjects. So I will discuss about the deposition process. I will discuss about the how to grow the quality films and how to make the efficient and the potential thin films. And these metal oxides actually have been chosen after the discovery of MOSFET in the year of 1960. So special attractions of these metal oxides because they have the relatively larger band gap, higher transparency in visible range, capability of absorbing the ultraviolet light, high conductivity and hole mobility. Again, they are producing the electron hole pairs, nice electrochemical response, good mechanical properties, and also the thermal stability. So these are the actually special characteristics gives these metal oxides for potential applications. So metal oxides are used for fabricating the transistors, sensors, lithium-ion batteries, energy storage, solar cells, catalytic and photocatalytic processes, non-volatile memory devices, tunneling devices, bioceramic, and antibacterial coatings, etc. So if we see that some devices, the photograph of these devices, because of these metal oxides widely used for the fabrication of sensor, biosensors, optoelectronic devices because of the low cost, high sensitivity, and simplicity in function. So like these are the cancer therapy, biosensors, glucose sensor, gas sensor, humidity sensors, battery, and fuel cell, optical lenses, transistors, and CD, optical coatings, These are the all devices based on that the thin film set. Here, if we see that the each metal oxide is sensitive to different gas. Different oxides materials have the ability to detect that the different types of the element, like the alcohol, hydrogen gas, oxygen, hydrogen sulfide, carbon dioxide. So the tin oxide is the most suitable for detecting these series of materials, compounds like the alcohol, hydrogen, oxygen, hydrogen sulfide, carbon monoxide. Indium oxide is especially used to detect the ozone, and zinc oxide is hydrogenated carbon and humidity sensors. So class of sensor materials includes these tin oxides, titanium dioxides, zinc oxides, ferric oxides, manganese oxides. These are the all common materials we used in our everyday life. Now I will talk about that the nanocrystalline material, nanostructure material, nanomaterials also that was given by the Richard Feynman from his discussions in the American Physical Society on an annual meeting in the year of 1959. He, the first author, actually discovered there is a plenty of room at the bottom. In his talk, Feynman presented ideas for creating nanoscale machines to manipulate, control, and image matter at the atomic scale. So these nanomaterials, the advantage and how to produce that the nanoparticles, nanomaterials, there are two ways: top-down process and bottom-up process. Top-down process is here, you see that the schematic image, the start with the bulk material and cut away material to make the what you want. So cutting the bulk material into small pieces, that this way you can create the nanoparticles. And on the other way, that bottom to up. Here, they're assembling of these all the building blocks, like such as the atoms, molecules, atom by atom, molecule by molecule, or cluster by clusters. So you can assemble these all the lighter elements into the bulk size. So that way is called that like the bottom to up way. You can create the nanoparticles, and from down to top, top to down, that is also the way to create that the nanoparticles. That nanoparticles is very simple. All of you have the very clear idea. You know that the surface area, right? Surface area to volume ratio is large for the nanoparticle. How to calculate that the surface area? If you consider that this is the 2 centimeter cube, this is the small box. What about the surface to volume ratio? 2 centimeter cube has the surface area how much? 24 centimeter square. 6 faces, right? So then you see that the 24 centimeter square. What is the volume? 2 to the power cube, that is the 8 centimeter cube. If you ratio that, make it ratio that 8 is to 24, that is 3 is to 1. If you consider this the cubic box of having that 10 centimeter size, what about the surface area? For the bigger the cubic box, 600 centimeter. What about the volume? 1000, that is 10 to the power cube. So what about the ratio? That surface area to volume ratio, 0 is to 6.1. So you see that the surface to volume ratio is always higher for the smaller the cubic size and the small particle. So that's why that we need that for higher efficiency and for better performance, then we need the nanostructure material. And these nanostructure materials have the speciality that surface area to volume ratio is very large. So when an object or cell is very small, it has a large surface area to volume ratio. How we can classify and the range of the nanostructure material in between the 1 to 100 nanometer, that we can say these group of materials, we can denote that as a nanomaterials in between the range 1 to 100 nanometer. The composition of nanostructures such as the monoclinic, monometallic, bimetallic, magnetic, metal oxide, semiconductor, hybrid, composite, etc. have been used frequently as the basis of their classifications. So different types of nanostructure materials we can fabricate easily in the laboratory. like in the form of the nanowires, nanofibers, nanotubes, nanobelts, nanofluids, nanoribbon, nanosprings, nanocapsules, quantum dot, nanosheet, nanocomposites, and nanoparticle. So these are the different morphology actually of these the nanoparticles material in the different shape. And here, if you see that the properties of the nanomaterials, as I am talking about the oxide material, ultimate my goal is to produce the nano crystallites material. So this bulk material to nanoparticles, if you can reduce the particle size, then that will increase that the properties of the surface area, increases the antibacterial properties, will increase the hardness, and increase also the electron band gap, electronic properties, and magnetic properties also. So these are the all advantages of the nanoparticle material if we can synthesize from bulk to the nano size. So in between 1 to 100 nanometers. So if we see that the process of fabricating that the nanoparticles, already I mentioned that the bottom up and top down process. These are the processes you see that the atomic molecular condensation, vapor deposition, sol gel process, spray paralysis, chemical electrochemical deposition process, aerosol process, and bioreduction process. That is the bottom up process. You can see then atomic and molecules to make the nanoparticle size. So these are the techniques we used to fabricate the nanoparticles. Again, from sputtering, chemical etching, thermal laser ablation, mechanical ball milling, explosion process. So that is the top-down process. From bulk to the nanoparticles we can do using the techniques. So these are all the common techniques. But in my presentation, I will talk about the spray paralysis process, as this is very simple, very easy, and very low cost, inexpensive technique, continuous process, and very low cost setup. Large area, scale area deposition we can do, easy to control, and also easy to fabricate. And finally, we don't need the vacuum system. So that's why I have chosen that the spray paralysis tactic. So anyone can make this a technique in the laboratory with the minimum expenses, few thousand rupees or taka, then you can make this system device in the laboratory, and you can grow that actually quality the films. That I will show all the deposited films was deposited by the homemade spray paralysis technique. So next I will show this. This is the process actually. You see that we need that the compressor, air compressor, and we need that the long channel is a capillary tube, and this is the nozzle. We can make it by a varied sheet, and this only the aqueous solutions is used as the ionic concentrations. That is the solutions we need. All the salts, those are soluble in water. That is the precursor solutions we prepare in a beaker, and it is connected with the needle, small needle. The borehole is 0.1 millimeter, and due to that, the pressure of the carrier air gas comes to this point, and it forces to the needle. The water is coming at the outlet of the needle and start to spraying the aerosols on the hot plate. So this is the way, and that depends on that the optimization of the good condition of the film. That is the D/L ratio. So that is easy to deposit the films on a larger scale area, because of depends on the distance. And the uniform film we can deposit on the hot plate. And the special advantage of this technique, we don't need that high quality the chemicals. We can deposit on the plain glass substrate, on plastic sheet, on paper, any low cost substrate that we can use, and we don't need the high grade the salt. And that is the advantage. We don't need the vacuum systems, especially the oxides thin films. That is the advantage for growing that the oxide thin films by the spray paralysis technique. So here, if we look at actually, what are the mechanisms actually for this the spray paralysis technique? You see that the aerosols or the subatomic particles, the solutions, ionic solutions are coming from top to the bottom. There are four forces involved here. Due to the gravitational force that pulling the all droplets downward to the hot plate, that is the gravitational force. And electrical force is responsible for making the bonds, and that is on the hot plate. That electrical force due to this electrical Coulomb force, that the all ions are joining together to form the bonds. Thermophoretic force is always, you see there is a high temperature at the bottom and the low temperature in the upstairs. So is always tendency to bounce off that the aerosol from the bottom to the up. So that force is also responsible. That is called the thermophoretic force. And stock force is the continuous flow of these aerosols from the nozzle to the hot plate, and that force is called the stock force. So these four forces are involved in forming the thin films on the plain glass substrates. Here we use that only the plain glass substrates. So these four mechanisms are responsible here. Next, actually, I will show that the techniques actually I will talk about after the deposition. Then these are the common techniques we used to characterize the quality of the films for special purposes, for application purposes. We need to characterize these the structural properties we need, and to calculate the structure of the compounds, the lattice parameters. Then the bonding characteristics we can get from the Raman spectroscopy. Surface morphology we can get it from the field emission scanning electron microscopy. And the elemental compositions and topographic study also we can do it from the AFM studies, and especially the optical band gap, the optical transmittance and energy band gap we can calculate from the transmittance data using that the UV visible near infrared spectroscopy. For electrical measurement, resistivity, that is also important, that we need that within the 10 kilo range, the resistivity, especially for using that the sensing purposes. So then Hall effect measurements, we do it actually to identify the type of the conductor, N type or P type, and also the carrier concentrations also we need it. Then hysteresis loop, for magnetic properties we can do it. So these are all common techniques. Even XPS also we can do it, and we need more other studies also, techniques, tools to characterize completely about the thin films. But these are the all commons available in our department. We are doing these techniques. Then the structural analysis. Then structural analysis, we need the powder XRD diffraction. Also single crystals X-ray diffraction to identify the single crystals. Here, what we measure that actually the XRD, powder XRD. We are measuring actually that the crystallite size. This is not the grain size, not the particle size. Particle is consist of lots of that the small the crystallites. So these are all the crystallites, and that is the interatomic distances that we calculate from the spacing from the XRD. So these are the bulk, that is the crystalline material, particle or grain consist of the small crystallites, and X-ray can see that the crystallites only, interatomic distances. So what we measure by that the XRD department, XRD, and that gives you that the crystallite size using the Scherer formula. So never we can measure that the particle size or the grain size. So the grain is either a single crystals or polycrystals material and is present either in bulk or in thin form, that is the grain. So this is crystalline material and small crystallites that we can measure using that the XRD. And from XRD, actually from the position of the XRD, that we can calculate the unit cell, and the peak intensity is also related to the atomic species composition and position of the atoms, and peak width also gives you the related to the size of the crystals. So the peak positions, peak intensity, and peak width. So these three parameters are very important. Especially the peak position gives you the purity of the material and unit cell size, and intensity gives you that the related to the composition of the material and position of the atoms, and the peak width gives you that the crystallite size. So this crystallite size can be calculated using this formula: strain, dislocation density, microstress, structure coefficient, lattice parameters. And these are the K is the shape factor, and monochromatic wavelength of that the X-ray, lambda, full width half maxima, Young's modulus, and D is the interplanar spacing. So these are the common equations we use for calculating the crystallite size. And definitely due to the doping into the crystals and bulk materials and the matrix of the common parent materials, then due to that dopant, there is always the strain and dislocation density microstress is there. So that we can calculate using this is the formula. Next, I will talk about that the common this material is a very promising material. Zinc oxides is still zinc oxides is giving that the unique properties because of this non-toxic material, highly transparent, good electrical properties, wide band gap, larger exciton binding energy. And next, this you see that this is the structure, Wurtzite structure, hexagonal. These are the zinc oxide material. And here, speciality actually this the spray paralysis technique. As far as I am talking about that, the spray paralysis technique, we need that the salts to dissolve in water, and this process is called the hydrolysis process. First of all, that is the process is for mixing that the salts with the water, and that is called the hydrolysis process. That ionization takes place, and ion are separated in the aqueous solutions, and then we use especially the zinc acetate or zinc chloride. Those samples are easy to dissolve in water. So that is the main consideration we have to take. So the zinc acetate dissolved in water and at the substrate temperatures, and then 200 degrees Celsius. And so by the spray paralysis technique, we have limitations actually. That as we are using that the plain glass substrate, so that stands up to the 500 degrees Celsius. So if we use the other the glass substrates, the borosilicate or silica and other, then we can go for high temperature. But normal substrate temperature is around 300 to 500 is enough to grow that the homogeneous, compact, the fine, smooth that the surface. And we use that there are some deposition parameters also. We need that some deposition parameters. And these are the, you see that the films on the substrate. How much that thickness of the films we can. That is the advantage by making that the concentration of the solutions, depositions, time, duration. So by varying that the deposition time and concentrations, we can tune that the thickness of the films. And we can grow 50 nanometer to 500 nanometer. That is possible. And that depends on that the deposition time and concentration. Normally, that the spray paralysis technique, we use the molar concentration, 0.1 molar concentration. This is the almost a standard. So 0.1 mole concentration of the precursor solutions we prepared, and we maintained that the temperature on the hot plate, that is the substrate temperature, around 300 to 500. And that temperature is required to decompose all the salts to form the solid structures and solid material, and as a coated material in the form of the thin films. So these are the things actually we did it actually. And then what we'll see, that is you see that the zinc oxides, and that is the fiber like network. And if we anneal the temperature from 300 to 400 degrees Celsius, then the fiber becomes more prominent. right? And very sharp and very clear. And again, if we increase that temperature 500, you see that the diameter of the wire fiber is becoming larger. So in our study, we observed that the very clear and narrower and the average diameter of the fiber is around 220 nanometers. So that is the films we have seen, and we have grown these the films by using that the homemade the spray paralysis technique. This is the spectrum. You see the transmittance data, and transmittance data. If you look at that, the sharp decrease of the transmittance is observed at around say the 350 or nanometer, and that is called the direct transition. So this material shows the direct band gap, and direct and indirect band gap. How we can estimate actually, how we can confirm. That is the one of the possible way to detect that from the transmittance data. If the transmittance data shows the sharp decrease of that the transmittance at around say the 350 or 375, and that is called the direct transition, because the strong absorption means that the incoming all photons have the sufficient energy to excite the electrons from the valence band to the conduction band. So that is the direct transitions, actually more absorptions here, and it means that the incoming all photon energies have the sufficient energy to excite the electrons from the valence band to the conduction band. This is the called the direct transition and direct band gap. If something you see here in the visible range, some small damping or small fluctuations, and that may be cause for the doping effect. That is called the doping effect. If there is a small damping nature, or that is the bumping or some oscillatory motions that you can see. Here the tau relations we used, you see that here the tau relations and extrapolate this the straight line to the x-axis, and that gives you the band gap energy. So these are the things for zinc oxides. We see that depending on that the thickness, and that we got that the refractive index is decreasing here, and the band gap is also decreasing, and that depends on the function of the tumor thickness. And you see here, this is the paper. We did it actually. That was the first paper actually from my lab in 2009, and that we got it. These all the nanofiber zinc oxides, very sharp and very clear and transparent. That is published in Crystal Research Technology. Till today, that citation is about more than 170 that we got it actually from our lab. Next, our target is to produce that the nano crystallite size, and that is the doping is the main role and effect to make that the crystallite size is small. From fiber is broken, and that is due to that the transition metal have the ability to make that the oxygen deficiency, and that the changing the oxidation number, and that the different properties of this the transition metal. Here we got it by doping that the cadmium in zinc and cadmium doped. Here we got it. You see that it is the small the grained particles here, and after doping the in atomic ratios actually we maintain this. So band gap engineering, actually we need to tune the band gap, and that depends. These are all the insulating materials characteristics here, less than the 5 electron volt. Only above the 5 electron volt, then we can say this is these are all the semiconducting nature. These are all semiconducting, and above 5 electron volt, that we can say this is the insulating characteristics. So these are the semiconducting behavior because of that the transition metals having that the odd number of electrons in the d shell. So that is the way, and we have tuned this the band gap, and that is also published in here is almost the Journal of Physical Chemistry, and that crystals we have grown in our lab. So everything is done here, and that in case of the zinc oxide alloying with the cadmium oxide is an effective means of decreasing the band gap energy. Next, I will show that the aluminum oxides films, that is also, you see that the substrate is almost the white, and that is the main small, very sharp and very compact and homogeneous distribution of these the aluminum oxides, thin films that have the special characteristics. On doping, actually, we have to think about that the ionic size. If it is comparable, then it can easily substitute, or a little bit the smaller or bigger, that can occupy to the lattice side of the iron, or it can, if it is comparable, then it can replace the iron is also. Here you see that the radius iron is here 0.69 or 67, and the aluminum is also here is comparable. I'm not sure here is. So this is the, you see that the pictures here. So the different compositions. So the pure iron oxides, that the 2, 4, 6, 8%. So ultimately, on an optimum condition, that gives you the certain values of maybe the 4 or 6 will give you the better performance, because of the larger surface area to volume ratio can absorb, and then better efficiency is also possible for the smaller crystallite size. These are the X-ray. Already I mentioned that the position, the intensity, and the width of this direction or plan, whatever we say. This is the indexing. That is the mirror index, mirror plan. That gives you that the position of the unit cell purity, and that is the intensity of the, gives you that the position of the atoms, and mainly the full width half maxima, that gives you the crystallite size. Due to that dopant, if that the peak is shifted, so there may be the small distortion, or that is called the lattice distortion, that from the standard the peak and the dopant XRD spectra, then we can see that the deviation or distortion of the lattice because of the doping effect, that we can calculate it here. That is also transmittance. Already I mentioned that sharp transmission of that the values gives you the direct band gap of the material. Here is the aluminum iron oxides. Already I have shown that the pictures. Next I'll show that the manganese oxide. Manganese oxide, you see, this is the without copper. So copper is a very cheap material, very low cost material, and easy to incorporate into the material matrix. So that copper we have chosen to doped with the manganese oxides, 2 atomic percent, 4 atomic percent, 6 atomic percent. You see that ultimate the gray crystallite size is a grain size is, or you can see that the small the crystallite size is reducing from higher to, these are all the agglomerated, and that is the cause of that the doping effect, and ultimately we have grown that the small crystallite size. Next slide, I will show that the titanium dioxide. Titanium dioxide is also very important material, have the different phases, and they have the both the direct and indirect band gap. Because of these material can transform from anatized to rutile and then brochite also. That depending on the phase transition, that the material, the single material can have the both the direct and indirect band gap also. Here you see that these are all the fiber structures, and these fiber structures is agglomerated here, and with the dopant of the zinc, and then ultimately small the particle size or the grain size that we have seen. But grain size and crystallite size is completely different. What we have seen from the SEM image, that is the grain, or that is called the particle size. But XRD, that gives you that the real crystallite size from the Debye-Scherrer equations. And here you see that the properties of these the titanium dioxide doped with the zinc. Here, these XRD tetragonal structures of anatase is strongly oriented along this 101 plan, and with the increasing that the zinc dopant, it becomes the compact, denser, and agglomerations at 6% is suitable. And here you see that the 0.68, the titanium, and zinc is 0.74, is more or less comparable. So they can substitute, that the zinc can substitute the titanium, and this way they can make the good the form properties of the films. The band gap is, you see that here doping concentrations 0, 2, 4, 6, 8% here. That is there is the blue shift here. We can say the band gap is increasing here. That is called the blue shift here. And what is the rule of that actually doping? We know that in between that the highest the electron density state of the valence band and lowest electron density of the conduction band, and in between this gap, that is the band gap, forbidden gap, and energy gap, and here is the Fermi energy level is there. So the rule of that dopant, the extra carrier, they can enhance that the Fermi level towards that the conduction band in such a way that the band gap is reducing here. And so here the zinc doped titanium, already I have shown that the values. Next I will show that the for tin oxides, that is our laboratory grown the tin oxides thin films. Here you see this is the films as deposited the pure tin oxides. And again, we have chosen that the copper as a doped material into the tin oxides. And you see, in presence of 2 atomic percent of copper, there is a porosity is developed. Porous structure is there. So, and again, if you see that the higher concentration for that the 4%, and that is the 6%. 4%, you see that the highly actually pinhole free, that the compact, dense, and the homogeneous distribution of this, the 4%. But for 5% here, you see that the some the hole and the crack and the some porosity is there. But the speciality is actually, if we want to fabricate the sensor material, we need that the porous structures, because the porous structures can absorb that the gas molecules. So the advantage of these the films as long as possible to produce the porous structures, and as well as the small crystallite size. These are all the criteria we need for sensing purpose, for application in sensing purpose here. So that is the image we got it on the tin oxides. Here, if you see that the doping concentrations versus the direct band gap, here you see that the band gap is reduces up to the 4%. That is the minimum, and then again the is increases, because the 4% is gives you that the better surface homogeneity and the compact. So that is the cause of getting that the low band gap. So next you see here the summary. We can see the pure thin films grain size is about 7.24 angstroms, and band gap is about here the 3.75, and the resistivity in the order of the 4. We got it actually this the resistivity is the plus, should be plus actually, maybe it's wrong, and the plus is always the resistivity, and conductivity in terms of that the negative here. So next we need actually that the 4-proof method to calculate the resistivity measurement here. So these are the equations. 4-proof method is very common. You know that the 2 terminal will be connected with the voltmeter, and 2 terminal will be connected with the emitter, and the spacings, and then we can measure that the electrical resistivity and activation energy here. So these are the mechanisms. You see that the rule of the grains, small the porous structure we need to absorb the gas molecule within the porous space. If it is the vertical size, then you see the gas molecules cannot trapped inside. Only the outer side that the gas molecule can trapped. So the mechanism is actually, you see that in connecting that the grains. So these are the outer actually the charge particle, and when these are the opposite the grains, 2 space charge layers back to back form the formidable barrier, and barrier is taking place because of that the in between the 2 grains, that side by side the charges layer, they make the depletions layer. So at the intergranular contact, 2 space charge layer back to back form the formidable barrier and for the elements to cross, and this gives rise to the higher resistance values at this contact point. So these are the contact points, but they are in the negative charge, they'll be opposed, and they make the barrier actually depletion layer. So these are the cause of creating that the resistance in between the small grains. So the basic principle of resistivity type the gas sensors is mainly we need that high sensitivity. These especially the tin oxides, that is the N-type material. And N-type material you see here, these are the low resistivity and high resistivity. In presence of that air, the oxygen, it gives the high resistivity. And here with the hydrogen, so that gives the low resistivity. The water molecules is also there. Here you see that the sensitivity increases with the roughness of the films. So we need always the rough, the surface material, so that can absorb the gas molecules. So sensitivity depends on that, the surface morphology of the material. Here, these are the spray paralysis deposition films consist of the nanograins. So we got it actually that the nanoparticles, nanograins, nanocrystallite size. And why these? We need that the hydrogen sensor, especially for these are the tin oxides films. The fuel cells will become the main energy store in our infrastructures. Our next generation depends on the hydrogen energy, fuel energy. So hydrogen has the larger diffusion coefficient with combustion range, small ignition carrier energy, and much more dangerous than the propane, butane, other gases. So continuous leakage monitoring is needed actually for uses, storage, and transportation of the hydrogen gas molecules. So here we need is always the market available, that the sensors available at the high operating temperatures, 300 to 400 degrees Celsius. But we need at room temperatures, because at high temperatures, that is the power consumption is more non-compatible with the silicon integrated circuit, and sensing may cause the ignition because of high operating temperature. So our attention, we strongly need the room temperature sensors for realization of one chief sensors highly desired in the hydrogen society. So then what we did it actually, these on the glass substrates, this is the milky white is the films, then the gold coated the films, transparent films, and then we measure the current versus the time, and depending the different oxygen, hydrogen, and argon mixing with the hydrogen gas molecule, and the ppm level, we measure that the 5000 ppm of hydrogen gas, and that for nitrogen and for oxygen is there. So that is can detect, because of that current values is increases because of the 5000 ppm level. And then again palladium coated the treatment, then the current and time versus you see here that the 550 ppm level, 500 ppm level, 5000 ppm level, that is the always the highest is 5000 ppm level. So the gas, hydrogen gas, is a sensitivity that we can detect from the sample. And you see that the rising time and recovery time. Rising time is the time taken to rise the maximum and to have the saturation, and recovery time to time from maximum to the minimum to reach, that is the recovery time also that. So 5000 ppm hydrogen at 200 degrees Celsius, so that samples we measure here. And these are the main sensitivity that we can detect as ground samples, and using that the transparent membrane here by using the gold and the palladium is also. Next, actually, we did on our samples that the glucose sensing, the behaviors also, we have seen that the glucose sensing, that is important for human body detection. The excess of glucose in the blood level may cause the damage of our health and life threatening. So that the glucose sensing is also important. Then we did it, the cobalt oxides films in our laboratory, cobalt oxides. Then you see that the cobalt oxides, you see here the pure cobalt oxides, then the 2%, 4%, and this is the 6% here. You see that 6%, 4%, 2%, 2% is here. You just keep in mind actually that the percentage, some dopant can go inside the interstitial side and substitution for making the good alloy, and maximum accommodation is possible about maximum the 15%. So the interstitial side they can go, and our main target to make the homogeneous, compact, and nano crystallite size, and that we got it. You see there, and the small crystallite size 4%, 6%, and that is also the small alloying is formed here, but the gradually is increases, and more roughness is also there at high concentrations. So from XRD that we did it actually to crystallite size and to confirm that the structures is the mainly this is mainly the monoclinic structures mainly. And here next our target as deposited that the main the cobalt oxide in cobalt oxides films, copper doped cobalt oxides. And here you see that the 4-probe method in presence of the solutions here, and that the 2 electrodes we use the copper and zinc electrode, and here is the film, and we measure in the indirect way that with the films in the glucose, without glucose in the film there is a connection, and in presence of glucose with the film there is the deviation, and sodium hydroxide is used to accelerate the solution, glucose solutions here. So next actually you see that this is the small this is the whole sample. This is the whole sample, and this is the semi-permeable membrane is used, the transparent coating in the solution of glucose, and in presence of glucose there is a resistance is measured, and without glucose there is a resistance is measured in this circuit. So that deviation gives us some the absorptions and the resistivity value. Resistivity may be increase or decrease, that depends on the nature of the films. So here if you look at that, resistivity is around 10 to the power 4 order, that is the quite reasonable within 10 kilo range, that the resistivity, carrier concentrations, and Hall mobility we measure. Rising time, response time, recovery time, that is the definitions already we got it. And here you see that the response time, you see that for this PU is 1.16, and that is for 2% is 1.09, and 4% that is 0.97, and that is 1.03. Out of these 4 data, we got that the minimum response time is that is the 0.97 for the deposition of 4%. If you look at the films and 4%, that is the definitely is you can see that is the better the films characteristics. So surface is more, so they can absorb the more. So these are the things data actually in our lab till we are working, and it is in progress to make the final data, and in that is in progress. All these data we got it, the recovery time and glucose response time. So and finally actually what I will say that actually we do, by depositing these the oxides, especially tungsten oxides, cobalt oxides, tin oxides, the addition of copper as dopant for optimization of the cobalt oxide particle for better sensing. And recently, these tungsten oxide and cobalt oxides are used actually for biosensor materials actually. Copper has a good catalytic activity, and as well as this is very cheap material, low cost material. Copper leads to greater absorption of oxygens for the detection of biocomponents. Copper can maintain the electrical resistivity as ionic radius of copper nearly equal to that the cobalt. So for doping, we have to choose that the ionic radius to be comparable. Then only can make these films is good quality and good bonding is also. Incorporation of cobalt ions by foreign divalent metal ions like the copper can result in spinal structures with enhance the catalytic activity of the material. So summary actually what I can say by spray paralysis deposition technique, we can deposit the very high quality films, very thick films, very rough films, very porous structures. This micrometer to nanometer range that we can deposit the films, and there is a low cost. There is no wastage of the material. The whole the ionic solutions we can use for the deposition. That is the main advantage. We don't need the vacuum systems, and we use the all the plenty of oxygens in the environment from the environment. So the especially the all oxides films are suitable especially for by the spray paralysis deposition technique. We succeeded in fabricating that the cobalt oxide, tin oxide thin films of glucose and hydrogen sensors. And here, low cost fabrication, no vacuum processing, low cost of substrates, any plastic, paper, even cloth or glass substrates that we can use. High optical absorption coefficient, suitable band gap for absorptions of sunlight. And finally, I would say that the SPD could be a simple route for the synthesis of nanostructures, thin films for gas sensing and optoelectronic applications. Here, actually, the title was that the metal oxide thin films and the state of the art and approaches. So these approaches is to use these the thin films as grown thin films, especially for detection purpose in the environment. That we can detect the environmental all signals incoming to the device, and they convert that signals into the detection. And so we can do it actually the thin films, and as well that is state of the art, especially main the purpose for application of thin films, the sensing purpose. We need the more porous, more rough surface and small crystallites, and that is possible by changing the deposition parameters. Actually, the substrate temperature is the one main parameter, air pressure is the second, and the flow rate is also, the concentration is also. So these are the all parameters we can control, we can tune easily. And that is also other purpose actually, that LED as grown samples that can be used for LED purpose is also. That part actually we did it in Ireland, Limerick University. That is also that as the active layer is the cadmium selenium sulfide, and these are the zinc oxides and nickel oxides, and as an electrode, and ITO on the glass substrate. So that we got it actually the first detection. I will not talk about that is the grown by the hot junction technique. And you just see that the SEM image, the cross-sectional, top-sectional view is the rod life shape. What is the advantage of the rod actually? If you can grow that the nanocrystallized spherical size, and this is the rod shape, and that is examined by, you see that the SEM structures here, that is the rod, the bullet shape, right? So this is the TAM image, and that is the SEM image, that the bullet shape. And that vertical size is always advantageous. That composition is detected by the that EDX data is also, the fluorescence lamp is used, that the LED, and we see that the broadening of that the peak, actually the intensity is the changes that depending on the different areas of the films actually. So these are the XPS for the bonding characteristics to identify. Here you see that the nano particles, if atomic percentage of these the nickel is about here that 41%, and that is the 59%. So the oxygens without heat treatment and with heat treatment is better. Here you see that the nanoparticles 41 that value is here. So under heat treatment is always is better. And these are the imaging spectrum actually for these the EDX distribution of here. You see the indium, tin, oxygen, nickel, zinc, sulfur, selenium, and cadmium. These are the all the spectrum for the distribution of that the dopant element. So this way, ultimately, we have seen that the laser spot, you see that is better when you increase that the cadmium, selenium, sulfur. This is the cadmium, selenium, sulfur is bright, and that is also small, but this is the quenching, is quenched. Even then, that gives you the luminescence. So that is the advantage of that for fabrication of this the LED light. So that is the purpose actually. We did it actually from Limerick University, not from BUET, but we have a collaboration and that is the advantage of this. You see that the selenium rich and selenium rich less. So is always you see that the condition is less is actually 25% ITO and better alignment and good alignment of. So advantage, finally, I would say the selenium rich is always gives you that the better. You see here that the you see here full width half maxima nanometer is here, full intensity is here 1500. So the to detect that the selenium rule of the selenium here. So these are the all the summaries and first detected, and that is also under investigation, not in details. So I would say the novelty of this work that is the first time detected with the cadmium, selenium, sulfur. That composition gives you the detection of the LED light, and that is the main collaborators of my research group. That is the PhD students Mehrnaz Sharmin, Muslima Jahan. They deposited the glucose sensing purposes and glucose sensing devices, and these are all the groups of working with the zinc oxides and titanium dioxides. And here also we are doing that the hard engineering tissue, hard tissue, that barium calcium barium titanate, that also group is working for making that hard tissue engineering. And that is the institutions is Limerick University, Barnell institutions for that the collaborative work of the LED light. And these are the groups the students are working in my lab, and that the Nandita Bishas is working at now in the Limerick University, and he did that the LED devices. And the all groups were working with these the metal oxides, the thin films. And this is 21 till today. We have that the publications is 6, and that is the 10th number already is accepted and in the printed form. So finally, I will thank you everybody for joining my presentations. And again, thanks to the Pabna University of Science and Technology, especially Dr. Pretam Kumar Das, for inviting me to give a presentation today. And I think this presentation will help to the beginners, those are working and will start research using that the low cost facilities in the department. We don't need that high quality and high sophisticated instruments. Even for doing the good quality films, that the spray paralysis deposition technique could be the best technique for growing the quality films. Again, thank you, the audience, for your patience hearing.
Thank you, sir, for your wonderful presentation. And the main aim of our program, I have already explained that our main aim is to motivate and encourage our students. And as you explained it, that your intention also to motivate the next generation researcher. And I'm very happy that by your lecture, some of our students have must have motivated, and we have got some question in inbox and in comments section. So if we allow, we can start our discussion session, sir.
Okay, I will try to answer if I can.
Okay, sir. Okay, so so the first question from the inbox, I'll take. So, what is the thermal dot? So quantum dot.
Quantum dot, actually quantum we cannot deposit actually that quantum dot, mainly that the particle and you see that small crystallites. Even then, these the smallest size that quantum refinement or quantum dot, that we cannot deposit that the spray paralysis deposition. That is the first that is the limitations. Quantum dot, definitely that is the smallest, the size of the in atomic size that can emit that the emission of that the energy excitation state, that we can define. But that spray paralysis deposition, so we can grow that the nanocrystallite size 20 to 50 nanometer, that is the minimum size. But that quantum dot that we cannot actually form using that the spray paralysis deposition technique. That we need the different techniques actually. Quantum dot is the full finement, actually the smallest, that is the possible, that is the size of the element to emit that the emissions from. That is not actually from spray paralysis depositions,
Okay.
as far as I know, actually.
So thank you. So we have another question. So what are the quantum wells and how quantum confinement takes its place in it?
Actually, that is the same questions. Actually, if we these as far as the spray paralysis depositions, that the limitations actually. Quantum confinement is definitely playing very important role for reducing that the band gap. That is also true. But what is happening actually in the films when the photon is absorbed, that photon phonon interactions and the electron hole carrier recombinations, this part. But for the fine quantum confinement is completely different. That is the features I have shown in my slides. So that is the limitations that I cannot actually say in details about that the quantum confinement. So the sorry, actually that part is the completely different and in different states of the matter.
Okay, sir. So we have another question. So question is why the morphology of film is such changed in between 4% and 5% of tin oxide film.
The reason is actually you see that all the unit cell there is a space, back end space, right? So, if we want to make it the dense film structure, that the doping element can go inside the interstitial site. Sometimes they can replace, sometimes they substitute. So, the 4% is the maximum accumulation of this doping element can make the good alloy. So what is happening actually in between the copper or iron or tin? So these are all the metals they are alloying actually. They are forming the alloy. So there is an optimum and the minimum. So reasonable is a too low concentration can not distribute in the whole the film surfaces. But 4% we found that the optimum to accumulate within the interstitial sites and substitutionals in the space and making the good alloy actually. If we make the more concentration, that makes the more defects, and that defects cause the reduction of that the increase of that the band gap is also right. To reduce the band gap, then we have to control that the nucleation sites. So the minimum concentration and optimum concentrations. So after doping 2 to 6%, then we got the surface morphology first, and then we measure the crystallite size, and then from that the optical transmittance and electrical measurements, then we got that 4% appears that the maximum optimizations of doping level and gives the better film features. So is always we cannot exceed that the more than 15%. Excess doping concentration goes to the outer side as in the form of the precipitation. So they will not gives the better performance. Is always try to make the good alloy to form the bondings, and by the substitutional and by increasing that the carrier concentration level, 4% we got actually the best, and that we observe from the optical images also. So is always you have to compromise. You have to start from the minimum and to maximum, and then from these different data you will get the best one from optical transmittance value, electrical resistivity value, and you can complement with the surface morphology. So these are the common actually this technique. Then only you can confirm this which percentage is the best for alloying alloy formation.
Thank you, sir. We have another question. So, what are the magnetic properties of confined d electrons in bulk transition metal oxide thin film?
Actually, this metal behavior only we can do if we use the cobalt, nickel, iron, that type of material actually. So this magnetic behavior is another properties we need if we use all the magnetic components. But especially for nickel or the copper oxide or the these manganese oxide, especially for these the sensor applications, we don't need that the magnetic characterizations. For sensing applications, we are using the tin oxides, right? Widely used zinc oxides. These are all the non-magnetic characteristics actually. So that's why these the magnetic properties only needs if you want to make the switching purposes, right? Diluted magnetic semiconductor switching purposes, magnetic switches and other performance, that we need that the magnetic studies. But especially if you want to make that the gas sensors or biosensors, then without the magnetic characteristics, that you can sufficiently make that the good device even without studying the magnetic properties. But magnetic definitely we need for that the spinning and the and as well as the Mosber effect and other studies for magnetic applications, magnetic switching, magnetic applications for magnetic materials. But I have mentioned the all materials mainly that the non-magnetic characteristics, especially for the gas sensing applications. So that's why that part is not included here.
Okay, sir, thank you. So we have another question. So what is the advantage of nanostructured zinc oxide thin film over a continuous zinc oxide thin film for optoelectronic application?
You see that the nanostructure, nanoparticles, whatever the zinc oxide or copper oxide or cobalt oxides, nanostructure means, first of all, you see that the surface to the surface area to the volume ratio is large. So it can absorb the more surface area, more absorptions, and better the electrical transportation properties, optical transportation properties. So that is the advantage for in the recent years why these metal oxides are taken more interest by the researcher, because of these metal oxides are capable of forming that nanostructures, nanomaterials, nanocrystallites, rather than the bulk. So if you can reduce the more to more nano size, then the more efficiency you can have. To achieve the more efficiency in the copper oxide or zinc oxides, then you have to reduce that the crystallite size. So that you have to tune actually, that how to reduce that the crystallite size. Then surface area will be more absorptions. Gas molecule can absorb the more absorptions, more transmissions, more transportations of electrical, optical, thermal, so electrical. So that's why that our main target that to reduce the crystallite size, and that crystallite size, if you can tune, if you can tailor that the crystallite size, then you have the more advantage. Because of, you see the in the first few slides you have seen that increases the activity, photocatalytic activity, antibacterial activity, electrical transportation activity. So always we prefer that the nanocrystallite size. That's why that nanoscience is getting more preference and is focused nowadays, right? Nanomaterials, nanosynthesis. Why this nanosynthesis, nanomaterials are now focused? Because of that advantage of that the nanoparticles.
Thank you, sir. This may be the last question. So, how to distinguish the small peaks of indirect band gap and exciton binding energy from absorption spectra?
Actually, these already I mentioned that you see that absorptions or transmittance, whatever you see that transmittance is more, absorbance is low, right? So you have to look at that the transmittance, the pattern. You are taking that the transmittance or absorbance in the range of UV to infrared range, 190 to 1100 nanometer. So if there is a tailoring or the sharp the decrease of that transmittance or absorbance is more, that more photon energy is absorbed, and that absorptions is capable of changing that the valence band to the conduction band easily. That's why we can identify from the transmittance data if there is a sharp transition in the range, whatever the visible or UV light, that direct sharp decrease of the transmittance value or absorbance, whatever that gives you that the indication of the direct bandgap material or indirect bandgap material. It's very rare some materials have the both the direct and indirect material, but especially the materials, most of the materials have the one band gap. So direct, that you can identify from the sharp decrease of the transmittance values in around the nanometer range, and that strong absorption, it means that a strong absorption, right? And that incoming photon from that the light have sufficient energy to excite the electrons from valence to the conduction band. This is the cause of having that the right. And another actually optical band gap energy is related to the size of the particles. Actually, size of the particle size that is also important rule for the energy gap measurement. Optical transmittance may be decreased if there is a contribution of the scattering because of the defect centers. If there is more defects, more scattering, and transmittance value will be low, right? So these and another causes of that, the donor density states also, that is also responsible for the decrease of the optical band gap, right? So age doping element, the nickel, copper, iron, whatever we are doping, actually that changes the actually substitution level, doping concentrations, and that is related to the formation of the oxygen vacancies and the gap and defect centers. These are all, many parameters are related for that the band gap decrease or increase. So what I will suggest that if there is a sharp decrease of the transmittance band, that indicates the direct band gap of that material. Easily you can say this is the direct band gap material.
Thank you, sir. As we don't have any more questions, so we should conclude our discussion session, sir. Thanks again, sir, for your wonderful presentation and discussion session, sir. As I have mentioned earlier, that the main aim of our program is to motivate our student, and I think we have doing our work since last 1 year by arranging international physics webinar, and we are going to celebrate our 200th webinar with a Nobel laureate speaker of 2018, Dr. Professor Donna Strickland. So dear student and the viewers, you are most welcome in our 200th episode of our International Physics Webinar. So thanks, sir, for helping us throughout this last year, and thanks again for giving me this opportunity to announce such an important webinar on metal oxide thin film, state of art and approaches. I think students and viewers have enjoyed it, and they might be fall in love in this research field and join in your group or in this field in near future, and develop these things and help our art.
Just a last sentence actually to the all participants. I would say actually the research is the searching of unknown material from the known material, right? Everything is known, but we are searching the unknown properties from the known material. So that I tried to explain actually the more basic and fundamentals. Still, I have some limitations. If I cannot satisfy to anyone, please consider it. So still I am working, and I will be very happy if some of you will start to think and to motivate your mind towards the research. That research comes actually by your dedication and by your sincere work, and one day definitely in Bangladesh we'll be able to fabricate all the sophisticated sensor devices, optoelectronic devices, with the contribution of our young generations. So আমরা প্রতিদিনই শিখছি, every day we are learning, and as a science student, even I am teaching more than 30 years, but I think every day I am learning. So lot of things actually you ask actually for this reduction of the band gap is caused by the reduction of the particle size, as well as for the quantum confinement effect. That quantum confinement effect is the different phenomena that have to go in a different way, not in that bulk and the thin film formations. That is the another concept for fabrication process. So anyway, that was my limitations. Maybe I could not satisfy you on that questions, but I am very happy to all of you to be present and to give a lecture under the invitation of the Pabna University of Science and Technology. And my special thanks again, once again, to Dr. Pretam Kumar Dash. Thank you, everybody.
Thanks, sir. Thanks, sir. It's my honor and privilege to host you in our International Physics webinar. Thanks again, sir. And I'd like to invite you to join our evening session with Donna Strickland on our 200th episode of this International Physics webinar, sir. So
Thank you.
Thank
you.
Yeah, sir.
Yeah. I'll try to attend. And namaskar.
Yeah, okay,
and
sir. Thanks.
thank you. So can I
Bye.
leave?